All right, so hello, my name is Łukasz and I work for Nordea, and today I'll be talking about how to build a blockchain. So raise your hands who knows Python. Yeah, and second question again about the blockchain. Do you know how it works, more or less? More or less. Okay. So, all right. So the technology that lies beneath blockchain is actually pretty simple, right? So there are things like public key cryptography, the one-way functions, the consensus, or proof of work. They are not really difficult to understand, but once they are combined, they form one of the most convoluted creations that we've seen in the last years, I think. So based on that, based on this simplicity, we can decompose the blockchain to the pieces and see how it works. So best to see it in action. So we'll see. Let's start. So first we start with the block. So its main purpose is to store the payload. So it has a couple of attributes, and right now we'll try to implement them. So we start with passing the index. Yeah, I can enlarge it. Yeah, it's fine. We have the index. We have the payload, which basically for Bitcoin, for example, they are the transactions that are stored on the block. And we'll take a parameter with the previous hash. So the hashing actually is a mechanism to chain the block together, to chain the blocks together. They are once they are added to the blockchain, thanks to that, they cannot be forged, and this is for this mechanism, for this to be done, we use the hashing, or we use in case of Bitcoin, it's a SHA function, and the hash of our current block is added to the next block, so that we can iterate over them and check if they are properly added and no block was modified. Okay, so we'll we'll take the timestamp and okay, so that's more or less what the block consists of. So now we need a function that will do the actual hashing, calculating that from those attributes. We need a library that will do the hashing. Now, because I'm on Python 3, then we need to convert some parameters to bytes. Sorry. Also, what we need to do here is to do this and Okay. Okay, so that's more or less the hashing function. So it takes all the parameters in their form and it hashes them and returns this digest. So actually, for that I use a spoiler which I prepared, just not to write everything. So this is more or less what I just written. Also the nice representation of the block. It will be nicely printed, and yeah, that's more or less how the block looks. So we'll take it. Nothing will happen right now. We just instantiated this, and in the next step, we'll add this to the blockchain. So for adding that, we need to define how the blockchain looks, right? So what is a blockchain? It's actually a linked list. The thing that links the items is the hash, actually. But in our case, we can store it simply in a Python list, and we'll do that. So okay. Sorry, self. And also, because the blockchain actually keeps track of the previous hash, the block itself knows its own hash, but it doesn't know the previous hash. The blockchain's duty is to add this to the current block in what it remembered from the last block. So we need to like have this tracked, so, right? So we need to track the previous hash. The initial one is empty, and we need to track also the index, which at the beginning it's 0, right? And we need a way to add a block to this blockchain. So we add the block with payload. So we pass our current index, we pass the payload that is being added for this block, and we pass the previous hash that we got from the previous iteration, right? So after having this block, we increase the index. We store the current hash so that it is included in the next block, right? And we, so it will be not payload, but self blocks, like that. And we'll our current newly created block to our list of blocks, right? So this is like a simple list of the blocks that we create, and we will return this block to C, right? So again, spoiler is better. It's more or less the same I wrote, but this function is, I won't write it, so that's how it to see. And we'll also take this class, and right now we can add our first block. So in case of Bitcoin, the first block was called the Genesis block. It contained a special payload, right? Just like that. So this payload actually was to indicate that this block was created on that specific date, and it is the headline from the Times at that day to remind us that the fractional reserve banking was not really good at that point. You know how it ended. So we'll add this, we'll create a new blockchain object. And we'll add the block. And let's see how it looks. Okay, Genesis payload needs to be also executed. And yeah. So we created our blockchain. It contains one block and this is the block actually which was returned. So if we print also the blockchain, we'll see that its height is now 1, right? So it contains 1 block. And, well, the last 5 blocks is being printed there, so there we have 1 block with the payload, with the hash of this current block, and it was created on that day, today. So let's add a couple more blocks to our blockchain. So we'll do call it payload. Okay. Sorry, it is the other way around. It should be like that. So we are adding the block with this specific payload. And we print that we added this block. And let's see, will it run? Yeah. So we added 10 blocks. Each of them has its own hash. And if we take a look at the blockchain at this point, it should contain all of them. So like 11 blocks, 10 plus the Genesis block. Last 6 blocks are that. And we don't print the previous hash. Maybe we will do that in here so that we see that the previous hash actually matches what we have. So once again that, and once again that, and once again that. And right now we can see, maybe from here, that in case of, this was the hash of the Genesis block, this is the hash that is stored here in the next block, right? Then this is the hash that is stored in the next block, and so on, right? So how can we verify that? We would need to go from the beginning and check if the next block contains the hash of the previous one, or if our current block contains the hash of the previous one. So again, this is a function that does that. I won't rewrite it, so just use a prepared one. And when we do that, we'll verify that the blockchain is valid. So here what happens, we take our current block and previous block from the blockchain's blocks, right? The current and the next one, let's say, and compare the previous hash to the calculated hash on the fly that does that. So what will happen if we try to forge one block? Let's say we take the block number 5, we take the payload, and we try to add some character to that. So how SHA 2height6 or any other one-way function works is that we are not able to modify even one bit of the contents of what was hashed, right? Because the hash will be completely different. And if we do that, then again, blockchain verification will fail on the block 6 actually, right? Because the block, we modify the block 5, but actually this will be detected on the next block because it won't contain the block which has this hash, right? Okay, so far so good? It's okay, understandable? Okay, now let's cover transactions. So what is a transaction? Let's say in Bitcoin again. It's simply a transfer of tokens from one address to the other, right? So to define a transaction, we will simply use name tuple in that case. It will be simpler to store that rather than a class, and it will contain the same data. We just need like the data class in Python 3.7, but right now we have to use the name tuple, or we could use a class, but I'll show you. So we define a transaction object or transaction class, and we call it transaction, and it contains address from, address to, and the amount. Right? This is how it will look. So the spoiler is the same. Okay. And we will add some transactions to our newly created blockchain, let's say. So I created some function that will add our transactions for the realistic addresses that were generated for the Bitcoin addresses, and we'll see how they look when we add them to our blockchain, and we'll try to verify that if it's properly added. So again, I will just take what was done here. Here, and yeah, okay, do that, and then I'll print the blockchain. So again, we added the Genesis block just to have this initial one. Then we added a couple more blocks with the transactions, right? So we have the payload for the first block, which contains transaction from this address to this address that transfers certain amount of coins, right? And again, we can verify that this blockchain is valid, right? So the hashes are intact and nothing was changed. Okay, so in such form, the blockchain is quite vulnerable, right? Nothing will prevent us at this step to just add some transaction and recalculate everything back, right? Change the hashes, and we can do that, and it will be again validated. So what needs to be done is to come up with some way to strengthen the blockchain in order to hinder the tampering of the blocks of the transactions, right? And this is achieved in a process which is called mining in case of Bitcoin. And what is mining, right? So mining is a computationally intensive task, right? Computers calculate something. They try to find a solution, right? A solution is something that, when applied to a block, the hash of the block fits the certain characteristic, let's say. Yeah? So in other words, we have two fields in a block, two new fields. One is called a nonce, and this is a numeric field which is being constantly increased. And upon each increase, the hash is being calculated. And once we reach a hash that has a beginning of the bits at the beginning start with a certain amount of zeros, then we say we found a solution. So for this nonce, the hash has zeros at the beginning, and it matches the set amount of zeros that we wanted to find for this block, right? So this amount of zeros is called a difficulty, right? Difficulty of mining. And process was designed this way to limit the amount of blocks that are created, right? So for difficulty 0, we can just calculate the blocks on the fly. There's nothing that prevents us from doing that. But for the higher the level of difficulty, the more work needs to be done in order to find this nonce that will fit that will make the hash fit the characteristic, fit the difficulty level, right? And due to how one-way functions work, we cannot like reverse engineer that. We cannot guess for this payload we will get this amount. So everything needs to be like brute forcefully calculated. That's the only way. And so based on the probability of getting the output every time, like we know that the output is we cannot guess that. So the only way that we can like limit the number of blocks that will arrive on the mean time in a certain amount of time is the difficulty level increase, right? So for Bitcoin, the agreement was that each block will arrive more or less in 10 minutes. And the difficulty level, right, to check that will be recalculated every 2016 blocks. 2016 times 10 minutes is 2 weeks. So every 2 weeks, the difficulty level is adjusted. So the more people arrive to the network and start mining, the level of finding the solution increases, right? The more effort is being put, the quicker the blocks are being like found, right? But every 2016 blocks, the algorithm takes last blocks, checks, okay, they were like found in a shorter time than the 2 weeks, and we need to find them in 2 weeks. So then we adjust the difficulty from the like simple computation to a certain amount of level that with the same level of computing power in the network, it should take then 2 weeks, right? Of course, it constantly increases, right? But it can also decrease, right? If the computing power from the network is taken away, then the difficulty can increase, can decrease, right? So what incentivizes people to join the network, to devote their computing power to join the network, right? The algorithm in Bitcoin is designed that each miner that starts mining can include in a new block a special first transaction. The first transaction is that they transfer some amount of coins from thin air, right, from some unknown address to their private address. And if the block is found, if they manage to find the solution, if they manage to find the nonce that matches the difficulty level, then they populate this block and the coins are basically theirs, right? Everybody agrees, everybody checks that this is a valid block, and the first transaction is also valid for them, right? That's how new coins are being created in time. So of course this all goes to the like next steps of the algorithm that is running for the miners, for the blockchain, and yeah, we'll try to simulate that right now. So again, I won't write this whole class on the beginning because it's a lot, but I will explain what changed from what we implemented last time. So in case of blockchain, I added this verification method which was created independently, and one thing that changed was the mining with a certain difficulty, which is also like remembered. So there is no algorithm for now that drives the difficulty level up and down, but it's set to a certain amount. And we, for the newly created block, we first need to do the mining in order to prove that we did that and we found the solution, right? With a set level of difficulty. What changed for the block is that we added one method for the mining. Mining, as I said, is very simple, right? So we simply check if we match the difficulty level with our current level. If not, then we increase the nonce, right? And how do we check that the difficulty matches? So Here it's a bit complex, but essentially what we get here from this line is that we get a string of bits from the hash. That's how it looks. It may be a bit complicated because here we converted each character to 8 byte string and then we combine that, right? So that's maybe the most complex line of code that there is. Then we take the number of bits that matches the difficulty level, so that we get a substring. We create another substring that has the same amount of zeros, and we compare them too. If they match, then the difficulty matches and the function stops. That's more or less how it looks. So those two attributes were added to our hashing method, right? So here we combine the nonce and the difficulty level with which this was mined into the hash, so that when the nonce is changed, we can check that easily. But once anything else is changed, so like somebody will try to forge the block and change the difficulty to decrease it, then it will also be detected, right? Because the hash won't match, and we'll check that in a second. So let's see how it works. So let's first see how the difficulty set to 0 works, right? So the initial level of difficulty we have here is 0, right? So when we create a new blockchain, we add some transactions and we see how much time it takes for those transactions and those blocks to be mined with this level of difficulty, right? Just take that. Okay, so time elapsed was 0, almost 0, probably some more, but it was like immediate, right? There was nothing difficult in finding those solutions because every like hash matched the characteristic. We didn't check anything, right? And we again have the transactions. We have the nonce, right? The difficulty set to 0, so we can see that everything was done. But what will happen if we change the difficulty level? So here. This is almost the same code, but the difficulty level is increased a bit, right? So hopefully it won't take us until the end of the presentation. Yeah, some time passed, right? And the time will be different each time, right? Because each time the blocks are different. The timestamp is different, right? So that's what it changes between them. In real world, the transactions will be different. And so each time of finding the block, each time it will be different, right? But it's not 0, right? If we would increase the level, it will take even more to find, right? And right now for Bitcoin, the difficulty is like 4 trillions, I think. 4 trillions. So it takes a lot of computing power, and that was, as it was said previously, the proof of work is really taking very, very high amounts of electricity in order just to find one block, one solution, right? Like one number, right? The nonce. Okay, so let's see what will happen if we'll change the difficulty in an existing block, right? We'll try to like alter the difficulty level. Essentially, what will happen? We will fail, right? We cannot change the difficulty once it was set and the block was mined with this level of difficulty. Same goes for the transactions. Right now we don't have to change the payload. We can simply try to add an evil transaction that will transfer like 1 million of coins from the victim or from somewhere to the hacker, right? So if we do that, the verification failed on the block area. So here I changed the difficulty on block 2. Here I changed the transaction 1. So it was detected even earlier that the hash doesn't match, right? And we have this evil transaction somewhere around here, right? Yeah, this is added, right? Yeah, so that's more or less how it looks. So is it difficult? Everybody understands, or there's some people that doesn't? Great, it's clear. Okay, so the conclusions is that there are a lot more details to that. So I just like scratched the tip of the iceberg due to lack of time for the full implementation of the things that run on top of blockchain of Bitcoin, essentially like propagating the transactions, for example. I haven't covered that. However, if anybody is interested, that the area to explore essentially is that. So how, for example, the transactions and addresses are validated using public key cryptography. Because here actually I added transactions like from manually, right? But in real world you need to like own those coins in order to spend them. And for that, the public key cryptography is used to validate that the transaction is owned by a certain address, and he can spend that, right? Another area is the distributed consensus, so how it works, how the 51% attacks work, right? How they are, how transactions propagated in the chain, how different nodes can come up with the same solution or the solution on their own for a different set of transactions, and how do they agree that the block that one of them found is the valid one, right? We saw that on the previous presentations that there are like splits in the blockchain, right? Some transactions, some blocks are being orphaned at some point, and we need confirmations to make sure that our block is the longest and our transactions won't be like discarded at some point. The transactions, how they actually work. Currently, we just like hashed the raw data from the transaction, but in real world, the block size is around 1 megabyte or even higher in different implementations, and it will take even more time to hash the whole transaction. So instead of hashing the raw transactions every time to find just one nonce, the Merkle trees are being used for that. So Merkle trees essentially take all the transactions and build up a tree-like structure. So in the end, from all of those transactions, there's just one hash, right? Then also mentioned on the previous presentation was the scripting of the Bitcoin. There is a script-like machine, which is not Turing complete in case of Bitcoin, so you cannot write real smart contracts on that. But still, it's interesting to see what you can do. For example, you can do 2 out of 3 signing of the transactions. So not one, but essentially 2 out of 3 existing private keys will be needed to make the transaction validated. So you can share keys with different people, with different stakeholders for those transactions to happen. And this can be done on the Bitcoin, right? And finally, there are other implementations. So as we saw, there was Neo, there was Ethereum, there's IOTA, which is completely different, has completely different foundation of how they are constructed. There, instead of the blockchain, we have the Tangle there. So it's also quite interesting to take a look at it. So yeah, that was more or less what I had in mind. So I hope you were enjoying this and understood at least something, and see right now that even though that it sounds difficult, it's not really difficult to understand the basics, but you need to like get your mind over everything that's on top. So all of those pieces fit together, and it takes quite some time to understand that. Thank you.